Welcome to Quietly Made. I am so glad you have found your way here tonight. This is a space for the curious and the weary, a place where we explore the vast, invisible infrastructures of our world, while giving your mind the permission it needs to simply rest. Before we begin, I invite you to join our community by subscribing and leaving a comment. I often wonder where these stories find you tonight. If you feel inclined, please leave a comment sharing what part of the world you are in and the hour you are settling into sleep. It is a small way for us to feel the quiet connection of this community, scattered across different time zones, but sharing this same moment of rest. If you fall asleep, that is exactly what should happen. You are safe here. You can always come back tomorrow and pick up exactly where you left off. Adjust your pillow. Take a deep, slow breath in and let it out. Let your mind drift as we begin. Before there was touch, there was distance. A gap, small but absolute, between the human hand and the machine it wished to command. In the earliest rooms built for calculation and control, this gap was filled with intermediaries, levers, dials, toggle switches with a satisfying, resistant click, rows of buttons pressed into steel housings, each one cold under the fingertip, each one requiring a small negotiation of force before it would yield. Picture such a room. Banks of consoles stretch along a wall, their faces dense with instrumentation. Needles tremble behind curved glass. Small bulbs glow amber, then red, then amber again. Each flicker a coded sentence in a language only the operator understands. The air carries a faint metallic warmth, the smell of components working quietly against their own resistance, of insulation slowly aging under steady current. Somewhere beneath the panel, a fan turns at a low, even pitch, a mechanical breath that never quite stops. The operator sitting before this wall of information does not touch the data directly. There is no direct line between intention and result. To move a cursor, a hand reaches for a separate device, a ball recessed into a housing, rolled beneath the palm, its motion translated through gears and contacts into an electrical signal that eventually, after a small delay, nudges a point of light across a distant screen. To select something, a finger finds a button, presses it down through a spring's quiet resistance, and waits for a corresponding click, a confirmation that the message has been received. Each action is mediated. Each intention passes through a chain of translation before it becomes visible. This was not seen as a flaw. For decades, it was simply how machines worked. The controls were built by engineers who understood switches and circuits, and they built interfaces the way they understood the world, as systems of discrete, mechanical events. A button was either pressed or not pressed. A dial pointed at one number or another. There was comfort in this binary clarity, this world of definite positions and confirmed states. The machine spoke back through indicator lights, through the gentle hum of drives spinning inside their housings, through printed characters emerging one at a time from a chattering print head, ink slightly wet, paper slightly warm from the friction of the strike. And yet, somewhere in these rooms, a quieter frustration was accumulating. As machines grew more capable, the layers of translation between a person's intention and a machine's response began to feel less like structure and more like friction. An operator training on a new console might spend hours simply learning which button corresponded to which function, memorizing a vocabulary of switches that had no inherent relationship to the tasks they represented. The machine did not care about the operator's intuition. It cared only about the correct sequence of mechanical events. A single missed step, a switch left in the wrong position, could send an entire process astray, and the operator would have to trace back through the chain of controls to find the error, checking each dial, each toggle, each small confirming light. In certain specialized environments, this friction became impossible to ignore. Operators tracking fast-moving points of light across a radar display needed to identify a target and respond within seconds, not minutes. Every second spent reaching for a separate device, adjusting a trackball, confirming a selection through a secondary button, was a second in which the situation on the screen could change. The interface itself, the layer of translation between eye and hand and machine, had become a bottleneck. It was not the machine's raw calculating power that limited its usefulness. It was the narrow channel through which a person could direct that power. Engineers in these settings began to ask a quieter question. What if the intermediary could be removed? What if a person could simply point at the thing they meant and have the machine understand that gesture directly without a chain of dials and switches standing between intention and result? It was a question asked without fanfare, in laboratories and workshops rather than public demonstrations. There was no single moment of realization. There was only a slow, accumulating awareness that the boundary between the human hand and the responsive machine had grown thinner than it needed to be, and that somewhere in that remaining space, a new kind of interface might be waiting to be found. The room hums on. The needles tremble behind their glass. But somewhere among the engineers watching these panels, a different picture is forming. A surface a person could simply reach toward and touch. The idea of a surface that could be touched directly did not arrive fully formed. It arrived the way most quiet advances arrive, as a series of small, unglamorous experiments conducted by people whose names would remain largely unknown outside their own institutions. What united them was not a shared blueprint, but a shared discomfort with the layers of mechanical translation that stood between a person and the information they needed to act on. Consider the physical reality these early researchers were working within. A cathode ray tube glowed in a dim room, its phosphor coating painting temporary shapes with each pass of the electron beam. A faint chemical afterglow lingering for a fraction of a second after the beam moved on. The glass was thick, curved, warm near its base, where the electronics did their quiet work. To point at something on this glass, a person's instinct was simple and immediate. Reach out a finger, touch the spot, indicate the location with the most natural gesture the human body possesses. But the glass, in these early years, understood nothing of touch. It only understood the electron beam sweeping across it, line by line, 60 times each second, a rhythm too fast for the eye to perceive as anything but a steady, continuous image. Some of the earliest attempts to close this gap did not use touch at all, but something adjacent to it. A light-sensitive device shaped like a pen could be held against the glass, and because it could detect the exact moment the electron beam passed beneath it, the system could calculate, through a small piece of timing logic, precisely where on the screen the pen was resting. This was not touch in the sense we would later understand it. It required a specialized tool, deliberately built and carefully maintained, its cable trailing back to the console like a tether. But it represented something important, an acknowledgement that the simple physical act of indicating a location deserved to be a legitimate form of input in its own right, not merely a novelty appended to a system built for buttons and switches. In separate rooms, separate researchers were approaching the same problem from a different physical principle entirely. Rather than sensing light, they began experimenting with sensing the electrical properties of the human body itself. The human hand, it turns out, carries a small but measurable electrical charge, an ambient field that shifts subtly whenever it approaches a conductive surface. Early experimenters built simple grids, wires arranged beneath a thin insulating layer, and found that when a finger drew near, the electrical characteristics of the nearby wires would shift in a way that could be detected and located. These early grids were crude by any later standard. They required careful calibration, produced inconsistent results across different rooms and different humidity levels, and often needed frequent adjustment by the very engineers who had built them. But the principle held. A finger with no special tool, no attached cable, no separate instrument, could communicate its position to a machine simply by existing near a prepared surface. The rooms where this work took place were unremarkable in every visible way. Fluorescent tubes overhead cast a flat, even light. Workbenches were cluttered with soldering irons resting in their stands, coils of hookup wire, small glass jars of components sorted by value. The prototypes themselves were often little more than a pane of glass or a sheet of transparent film, wired at its edges to a breadboard dense with resistors and capacitors, the whole assembly connected by a tangle of colored LEDs to an oscilloscope whose green trace would jump and settle each time a finger approached the surface. There was no polish to any of this. No enclosure hid the wiring. No smooth casing disguised the improvisation. What existed was function, tested and retested, a slow accumulation of small proofs that the idea was sound, even if the engineering was still rough. Progress moved through published papers, internal reports, and demonstrations given to small audiences of colleagues who understood how significant a small improvement could be. There was little sense in these rooms that a broader public would one day interact with surfaces built on these same principles. The researchers were solving a narrow problem: how to let a person indicate a location without the friction of an intervening device. The rest, if anyone considered it, was secondary to the satisfaction of watching a crude grid of wires correctly register a fingertip, again and again, in a quiet room lit by fluorescent tubes and the soft green glow of an oscilloscope trace. To understand how a touch could be sensed at all, it helps to slow down and consider what a touch actually is, physically, at the scale where these early machines operated. A fingertip is not a simple point of contact. It is a soft, slightly moist surface, warmer than the surrounding air, carrying a faint electrical charge distributed unevenly across its ridges and valleys. When this fingertip approaches a conductive surface, it does not merely rest there. It alters the surrounding electrical field in subtle, measurable ways. The way a stone lowered into still water displaces the surface without needing to touch the bottom of the pond. Early researchers realized that if they could build a surface sensitive enough to detect this displacement, they would not need mechanical contact at all. Proximity itself could become a signal. This realization led to two distinct families of approach, each with its own internal logic, its own materials, its own failure modes. The first family relied on capacitance, the subtle shift in an electrical field caused by a nearby conductive object. A grid of fine wires, or later, a thin, transparent conductive coating applied to glass, would carry a small, constant electrical charge. When a finger drew near, it would draw a minuscule amount of that charge toward itself, and this tiny drain could be measured and located. The elegance of this approach lay in its lack of moving parts. Nothing needed to bend, flex, or compress. The surface could remain perfectly rigid, sealed, protected from dust and moisture, while still registering the presence of a finger through the glass itself. The second family relied on resistance rather than capacitance, and it required physical contact rather than mere proximity. Here, two thin, flexible layers were separated by a nearly invisible gap, each coated with a conductive material and each carrying a small current. When pressed together, at the exact point of contact, the two layers would touch, completing a circuit at that specific location and allowing the system to calculate, through careful measurement of voltage, precisely where the pressure had occurred. This approach had a distinct advantage. It could be triggered by anything capable of applying pressure: a fingertip, a gloved hand, a blunt stylus, a fingernail. It did not require the electrical properties of human skin at all, only physical force distributed across a small enough area. Each approach carried its own texture, its own feel beneath the hand, even in these earliest laboratory forms. A capacitive prototype, when finally assembled into something a person could touch, offered almost no physical feedback at all. The glass felt smooth, cool, entirely unyielding, and the only evidence that a touch had registered came from a distant readout, a needle swinging on a meter, or later, a small light blinking on an adjacent panel. There was something almost eerie about it in these early demonstrations, a surface that seemed to know it had been touched without ever appearing to move, without offering the fingertip any of the small resistances the hand had come to expect from a physical world built on friction and pressure. A resistive prototype, by contrast, offered a faint but perceptible give beneath the finger, a softness that came from the thin gap between the two conductive layers. Pressing against it felt closer to pressing against a taut membrane than against solid glass, a small yielding that most users, even decades later, would come to associate with the particular feel of resistive touch surfaces. Engineers working with these early prototypes noted this difference carefully, understanding that the physical sensation of touch was not incidental to the technology, but an inseparable part of how a person would eventually judge whether an interaction had succeeded. In laboratory notebooks from this period, entries were sparse and technical, recording voltage readings, describing the fabrication of successive prototype layers, noting failures where a coating had been applied unevenly and produced dead zones where no touch registered at all. There was no anticipation in these pages of how widely these two families of technology would eventually spread. There was only the steady, careful work of comparing one approach against another, refining materials, adjusting the thickness of conductive coatings by fractions of a millimeter, and slowly building towards surfaces reliable enough to leave the laboratory bench and enter something resembling a working device. Materials in this era of early experimentation were rarely purpose-built. Researchers worked with what existed, adapting components designed for entirely different applications, coaxing them toward a new function through patience and repeated trial. Transparent conductive coatings, a thin metallic oxide applied in a layer so fine it remained nearly invisible to the eye, had originally been developed for other optical purposes entirely. Someone, in a quiet moment of lateral thinking, recognized that a material capable of conducting electricity while remaining transparent to light was exactly what a touch-sensitive overlay would need. The glass beneath it could remain visible. The display behind it could still be read clearly, while the coating itself carried the small electrical signals necessary to detect a fingertips approach. Applying this coating evenly was its own quiet craft. Too thick, and the transparency suffered, casting a faint haze over whatever was displayed beneath. Too thin, and the electrical resistance across the surface became inconsistent, producing readings that drifted depending on where exactly a finger made contact. Technicians in these fabrication rooms worked in conditions of careful cleanliness, aware that a single speck of dust settling onto a surface before the coating was applied could create a permanent flaw, a tiny dead zone that would never register touch correctly, no matter how the surrounding electronics were calibrated. The rooms themselves often carried the faint, particular smell of solvents used to clean glass substrates before coating, a sharp, slightly sweet odor that lingered in the fabric of lab coats long after a shift had ended. Early prototypes were rarely elegant. A researcher might carry a sheet of coated glass to a workbench, its edges taped rather than properly framed, wires soldered directly to the corners of the conductive layer, with a bead of solder just large enough to hold, but not so large as to short the delicate coating beneath. These prototypes were tested against oscilloscopes that traced the changing voltage in real time, the green line on the circular screen jumping and settling with each touch. a visual translation of an invisible electrical event happening beneath a fingertip. Success in these tests was measured in small increments. A touch registered consistently across repeated attempts, a dead zone identified and mapped, a drift in baseline readings traced back to a fluctuation in room temperature or humidity that the electronics had not yet been designed to compensate for. Styluses appeared early in this history as a practical compromise, a way to achieve precision that a broad fingertip could not easily provide. A narrow tip, whether passive or carrying its own small electronic signal, could be tracked with far greater accuracy than the diffuse contact area of a human finger. And for tasks requiring fine detail, drawing a precise line, selecting a small element on a crowded display, the stylus offered an obvious advantage. Some early systems were designed exclusively around stylus input, their sensing grids fine enough to track a narrow tip but too imprecise or too specifically tuned to reliably register the broader contact of a bare finger. This design choice would echo forward for decades, a quiet fork in the technology's development between systems built for precision instruments and systems built for the more universal, more immediate language of the human hand. Reliability testing in these early years involved a peculiar kind of repetitive labor. Engineers would tap the same point on a prototype surface hundreds, sometimes thousands of times in succession, watching for any drift in the recorded coordinates, any degradation in the underlying coating from repeated contact, any sign that the materials chosen would not withstand sustained, ordinary use. Some coatings wore thin after only a few hundred contacts, the conductive layer scratching away under the friction of repeated touches, leaving faint, pale lines where fingertips and styluses had worn a path across the glass. Other formulations held firm through thousands of repetitions, showing no visible wear even under close inspection with a magnifying lamp. And it was these formulations, quietly identified through patient, unglamorous testing, that would eventually prove durable enough to leave the laboratory behind and enter the far more demanding environment of continuous daily use, carried in pockets, pressed by countless different hands, exposed to dust and moisture and the small oils that every human fingertip leaves behind. No single laboratory owned this technology. That is the most important thing to understand about the years that followed the earliest prototypes. Progress did not move in a straight line from one inventor to the next, each passing a completed baton forward. It accumulated instead, unevenly, in dozens of separate rooms across different institutions and fields, each group unaware of how far the others had traveled, each solving a slightly different version of the same problem. A research group focused on air traffic control might refine a capacitive grid capable of tracking a single fingertip across a radar-like display, motivated by the narrow, urgent need to let controllers select and identify aircraft without reaching for a separate keyboard. A university laboratory, working under an entirely different funding structure and an entirely different set of goals, might pursue similar principles purely as an academic exercise in human-computer interaction, publishing findings in journals read by a small, specialized audience of researchers, rather than by any engineer building a commercial product. A private company developing specialized industrial equipment for factory floors where workers wore heavy gloves and could not reliably operate small buttons might independently arrive at a resistive touch approach, valuing its ability to register a press through fabric or leather, a durability that pure capacitive sensing at the time could not match. These parallel efforts occasionally intersected through published papers that crossed disciplinary boundaries, through conferences where researchers compared notes over coffee poured from steel urns into thin paper cups, through patents filed and later cited by engineers an ocean away who had never met the original inventors. Ideas moved slowly in this era, carried by physical documents, printed journals mailed between institutions, microfiche copies retrieved by researchers willing to spend an afternoon scrolling through reels of film under the dim glow of a reader's lamp. A discovery made in one laboratory might take months, sometimes years, to reach and influence a researcher working on a parallel problem elsewhere. And yet, despite this slow and fragmented pace, a kind of quiet convergence was occurring. Independently, in laboratories that shared no direct connection, researchers were arriving at strikingly similar conclusions about what a workable touch interface required. It needed to be durable enough to withstand thousands, eventually millions, of individual contacts without degrading. It needed to be transparent enough not to obscure whatever information was displayed beneath it. It needed to respond quickly enough that a person touching the surface would perceive the response as immediate, without any perceptible delay between the physical gesture and the corresponding change on the display. And it needed to be simple enough in its underlying mechanism that it could eventually be manufactured at a scale far beyond the careful, individual craftsmanship of a laboratory bench. This last requirement, the question of manufacturability, would prove to be the quiet bottleneck holding back everything else. A prototype that worked reliably in a controlled laboratory setting, tested by a small number of careful researchers under stable temperature and humidity, was a very different object from a component that needed to be produced identically, thousands of times over, by workers on a production line, using materials sourced from external suppliers whose consistency could not always be guaranteed. The accumulation of scientific understanding was, by this point in the technology's history, substantial. What remained was the harder, less glamorous work of translating that understanding into something that could be built again and again at scale, without the individual attention a laboratory prototype could receive. Consider what this translation actually required. A laboratory technician assembling a single prototype could inspect every coating by eye, test every connection with a meter, and set aside a flawed sheet of glass without a second thought. A production line offered no such patience. Machines needed to apply coatings evenly across large sheets of glass, moving at a constant pace. Inspectors needed methods for catching flaws quickly, without pausing the line for the careful scrutiny a laboratory bench allowed. Every material substitution, every shift in ambient humidity within the factory carried the potential to introduce inconsistencies a controlled laboratory setting had never needed to account for. The accumulation of knowledge was ready. The infrastructure required to carry that knowledge into ordinary hands was still being built. If the first half of this accumulation was about scientific principle, the second half was about something quieter and more stubborn. The accumulation of small, practical fixes, each one addressing a flaw that only became visible once a prototype left the bench and was handled repeatedly by someone other than the person who built it. This is where a technology's real character begins to emerge, not in the moment of discovery, but in the long, patient process of discovering everything that discovery did not yet account for. Take the question of what happens when more than one thing touches a surface at once. A laboratory researcher testing a single prototype with a single steady fingertip might never encounter this problem. But hand the same prototype to someone unfamiliar with it, and they might rest a second finger against the edge of the frame without thinking, or lean a sleeve cuff against the lower corner of the glass while reaching for something else. Early sensing grids, tuned to detect one clear point of contact, could become confused by these secondary, unintended touches, sometimes registering a location halfway between the two contact points, sometimes refusing to register anything at all until the extraneous contact was removed. Engineers began to understand that a working interface needed to account not just for the touch a person intended, but for the touches a person did not realize they were making. Temperature and humidity, too, proved to be quiet adversaries. A capacitive surface, calibrated carefully in a climate-controlled laboratory, might behave differently entirely once installed in an environment with fluctuating heat, or in a room where the air carried more moisture than the laboratory ever had. The baseline electrical readings the system used to distinguish a genuine touch from background noise would drift, sometimes by amounts too small to notice on any given day, but large enough, accumulated over weeks, to render a once reliable surface inconsistent. Solving this meant building in compensation, small circuits that continuously recalibrated the baseline, watching for slow drift and correcting for it automatically, rather than relying on a single fixed calibration set once in a laboratory and never revisited. There was also the matter of what a surface looked like beneath ordinary light, rather than the controlled lighting of a demonstration room. A transparent coating that appeared clear under a laboratory's even fluorescent glow might reveal a faint rainbow shimmer under direct sunlight, an optical interference pattern caused by the coating's thickness interacting with visible light in ways the original designers had not anticipated. Correcting this required adjustments not to the electrical properties of the coating, which remained sound, but to its physical thickness and composition, a delicate rebalancing between optical clarity and accurate sensing. These were not separate problems. They were entangled, each adjustment to one property nudging the other in ways that required careful, iterative testing to fully understand. Slowly, across many separate research groups, a shared body of practical knowledge began to form, even without formal coordination between them. Certain coating thicknesses proved more forgiving than others. Certain edge sealing techniques kept moisture from creeping beneath the conductive layer and corroding it from within. Certain calibration routines, run automatically each time a device powered on, could compensate for most of the drift that temperature and humidity introduced. None of this was glamorous work. It rarely appeared in the published papers that later histories would point to as milestones. But it was this accumulation of unglamorous, practical understanding, tested against the ordinary imperfections of ordinary rooms, that would eventually make it possible for a touch-sensitive surface to leave the laboratory and survive contact with the wider, less controlled world. Picture the technicians who carried out this quiet correction, hunched over workbenches late into the evening. A single desk lamp casting a warm circle of light across a cluttered surface of tools and half-finished prototypes. A multimeter's probes rested against two solder points, its display glowing faintly, numbers shifting as a gloved finger presses and releases against the surface under test. A logbook lies open nearby, filled with small, careful handwriting, columns of measurements taken under different conditions, each entry a tiny data point in a slowly forming picture of how this new surface actually behaved once removed from an idealized laboratory. There is no urgency in these entries. There is only the steady accumulation of understanding. One measurement, one correction, one small improvement at a time. A touch surface, however refined, is only half of an interaction. The other half is the machine's response. And in this era, that response was still overwhelmingly mechanical. To understand what it felt like to use one of these early touch-enabled devices, it helps to set aside any modern assumption of instant, silent reaction, and instead imagine a small orchestra of moving parts working together behind the glass, each contributing its own sound, its own timing, its own presence to the experience of a single touch. Consider a display of this period, built not from the thin, flat panels that would come later, but from a cathode ray tube housed in a deep, heavy casing. The tube required a significant electrical charge to operate, and switching a device on meant listening to a rising hum as internal capacitors charged, a faint, high-pitched whine that settled after a few seconds into something closer to silence, though never quite true silence. Behind the touch surface, this tube painted its image the same way it always had, an electron beam sweeping in tight horizontal lines from top to bottom, each pass leaving a brief phosphorescent glow that faded just before the next pass renewed it. If you touched the glass and expected the image beneath it to respond, you were waiting for a chain of separate systems to communicate. The touch sensor detecting your fingertip, a controller translating that location into coordinates, a processor consulting whatever logic determined what should happen next, and finally the display circuitry, redrawing the appropriate portion of the screen. Each link in this chain took time, fractions of a second individually, but accumulating into a delay a careful observer could notice, a small gap between the moment of contact and the moment of visible response. The devices that housed these components carried a physical heft later generations would find unfamiliar. Metal chassis, sometimes steel, sometimes cast aluminum, provided structural rigidity and a significant portion of the device's overall weight. Ventilation slots, cut directly into the casing, allowed heat to escape, and holding a hand near these slots after a device had been running for some time revealed a steady, warm exhale of air, evidence of the electrical work happening continuously inside. Internal fans, where present, added their own low hum to the device's sound profile, a steady mechanical breath running beneath whatever interaction was taking place on the surface above. Buttons, even on these earliest touch-enabled devices, had not yet disappeared. Physical switches persisted alongside the new touch surface, often handling functions considered too critical to risk on an interface still viewed by many engineers as experimental. A power switch retained its familiar mechanical toggle, offering the satisfying, unambiguous click of a physical state change, a confirmation no touch surface of this era could fully replicate. Volume controls, where present, often remained physical dials, their resistance calibrated by hand during assembly, adjusted until the movement felt neither too loose nor too stiff beneath a thumb. This coexistence of old and new was not seen as a contradiction. It was simply the sensible acknowledgement that a new interface, however promising, had not yet proven itself reliable enough to bear the full weight of every function a device needed to perform. There was a particular texture to operating one of these hybrid machines, layered, almost like handling two different eras of engineering fused together. Beneath your fingertip, the touch surface offered its faint, cool smoothness, or its slight resistive give. Surrounding it sat the familiar architecture of mechanical control, a rocker switch for adjusting brightness, its edges rounded from use, a small red indicator light glowing steadily beside it. Opening a panel to access an internal setting often meant sliding a small door aside, feeling the faint click of a plastic catch releasing, revealing tiny, recessed switches that required the tip of a pen to adjust, since fingertips were considered too imprecise for such fine work. The sound of these devices carried its own particular character, a relay clicking somewhere deep inside the chassis as a mode changed, the faint mechanical whir of a small motor adjusting an internal component, a cooling fan shifting to a higher speed as internal temperatures climbed. Even touching the screen itself sometimes produced an almost imperceptible tick as certain resistive layers made contact, a tiny acoustic signature of two conductive layers meeting beneath a fingertip's pressure. None of these sounds were designed deliberately. They were the natural byproduct of mechanical and electrical processes happening in close proximity, an ambient soundscape anyone working with these machines would come to recognize as the ordinary background music of getting something done. The people who built these early devices were, in a real sense, translators, working at the boundary between two different engineering traditions that did not always speak the same language. On one side stood the world of mechanical and electromechanical design, a discipline with decades of accumulated practice in switches, relays, and moving parts, where reliability was measured in the number of times a physical mechanism could cycle before wearing out. On the other side stood the newer, quieter world of solid-state electronics and sensing surfaces, where reliability was measured differently in electrical drift, in signal-to-noise ratios, in the consistency of a coating applied at a molecular scale. Bridging these two traditions required engineers fluent in both, and in the early years of touch-enabled devices, such engineers were relatively rare. Assembly, in these years, remained a largely manual process, carried out on factory floors where workers sat at long benches, each responsible for a particular stage in a device's construction. A worker might spend an entire shift attaching connector wires to the corners of a touch panel, a task requiring careful, repetitive precision, since a poorly soldered joint could introduce electrical noise that would only reveal itself much later during final testing, by which point tracing the fault back to its origin required patient troubleshooting. The rhythm of this work had its own particular cadence, the hiss of a soldering iron touching flux, the faint acrid smell that rose briefly into the air before dissipating, the soft click of a completed panel being set aside into a tray for the next stage of assembly. Testing these assembled devices before they left the factory involved its own careful choreography. A finished unit would be connected to diagnostic equipment, cables trailing from ports along its edge to a bank of testing instruments arranged on a nearby cart. A technician would run through a sequence of touches across the surface, following a printed checklist, verifying that each region of the panel registered contact accurately, that no dead zones had emerged during assembly, that the underlying display responded within an acceptable window of time. Devices that failed this testing were set aside, not discarded, but returned to a separate bench where a more experienced technician would attempt to diagnose the specific fault, sometimes tracing it to a single cold solder joint, sometimes to a coating applied slightly too thin in one corner, a flaw invisible to the eye but clearly evident once the diagnostic equipment registered an inconsistent reading in that exact location. There was, in this period, a growing recognition that the mechanical and the electronic needed to be designed together from the earliest stages of a product's conception, rather than treated as separate systems bolted together after the fact. A touch panel could not simply be dropped into an existing mechanical housing designed for an earlier generation of buttons and switches. The housing itself needed to change, needed to account for the particular electrical shielding, a touch sensor required to avoid interference from nearby components, needed to provide the correct spacing between the sensing layer and the display beneath it, a gap measured in fractions of a millimeter that, if wrong, could introduce a visible parallax between where a finger touched and where the corresponding action appeared to occur on screen. This coordination between mechanical housing and electronic sensing marked a quiet but significant shift in how these devices were designed, moving away from a world where interfaces were added to machines and toward a world where the interface and the machine were conceived as a single, integrated whole from the very beginning. This shift required patience, not least from design teams who had spent years refining mechanical housings according to principles that no longer fully applied. A structural engineer accustomed to designing a casing around heat dissipation and durability now had to consider an entirely new variable: the electromagnetic environment surrounding the touch sensor, and how a seemingly unrelated component, a power supply routed too close to the sensing layer, could introduce a faint interference that manifested as an occasional, unexplained jump in registered touch position. Solving this meant repositioning components that had, in earlier designs, simply gone wherever space allowed. Documentation from this period reveals a workforce gradually developing a shared vocabulary for problems that had not existed a decade earlier. Terms describing electrical noise and coating uniformity began appearing alongside the older language of mechanical tolerance and material fatigue, one engineering tradition slowly absorbing and reshaping the other. Every emerging technology eventually reaches a quiet, unglamorous turning point where the interesting problem is no longer whether something can be built, but whether it can be built the same way twice. For touch-sensitive surfaces, this turning point arrived gradually, spread across years of accumulated manufacturing experience, as separate companies and research groups began comparing notes, sometimes formally through industry associations, sometimes informally through the ordinary movement of engineers between employers, each carrying with them the particular lessons learned at their previous workplace. Standardization, in its earliest form, was less about agreement and more about convergence. Different manufacturers, working independently, tended to arrive at similar solutions when faced with similar constraints, simply because the underlying physics left only a limited number of workable approaches. A conductive coating needed to fall within a certain range of thickness to balance transparency against electrical performance. And this range, dictated by the properties of the materials themselves, rather than by any formal agreement between companies, meant that manufacturers across different countries, using different equipment, often converged on remarkably similar specifications without ever directly comparing notes. This kind of natural convergence, driven by shared physical constraints rather than deliberate coordination, formed the earliest and most fundamental layer of standardization in the industry. Formal standardization followed later, driven less by physics and more by the practical demands of a growing supply chain. As touch panels began appearing in more varied products, manufacturers of the panels themselves became increasingly separate from manufacturers of the devices those panels were installed into. This separation created a need for shared specifications, common language describing exactly how a panel should behave, what electrical signals it should output, what physical dimensions and mounting points it needed to conform to, so that a company building a device could reliably source panels from multiple suppliers without redesigning the surrounding housing each time. Industry working groups formed around these questions, bringing together representatives from competing companies who found, despite their competition in the broader marketplace, a shared interest in agreeing on basic technical compatibility. A panel built to a common specification could be evaluated, tested, and integrated using shared procedures, reducing the burden on every company in the supply chain rather than benefiting any single participant exclusively. These early standardization meetings, held in conference rooms in office buildings scattered across different cities, carried a particular procedural formality. Engineers presented technical papers describing proposed specifications, defending their reasoning against questions from competitors who had every incentive to find flaws, since a poorly designed standard adopted industry-wide could create problems for years to come. Debates over seemingly minor details, the exact voltage range a panel should output, the precise tolerance allowed in a mounting hole's diameter, could stretch across multiple meetings, each side bringing data from their own internal testing to support their position. There was nothing romantic about this process. It was slow, occasionally contentious, and driven by the unglamorous but essential recognition that an industry could not scale on the strength of individual companies pursuing entirely separate, incompatible approaches. The physical evidence of this work can be found in the quiet uniformity of components that seem, at first glance, unremarkable. A connector at the edge of a touch panel, with its particular number of pins arranged at a particular spacing, might appear to be simply the way such connectors have always been made. In truth, that spacing was the product of extended negotiation, manufacturers gradually narrowing toward a single agreed design robust enough to be manufactured reliably by separate companies using different tooling. Once adopted, such a standard rippled outward through the supply chain, influencing the testing equipment, the assembly machinery, and the training given to technicians who would spend careers working with components built to a shared specification without ever needing to know the history of meetings that had produced it. Trade publications from this period occasionally reported on these efforts in dry, technical language, announcing the finalization of a specification, the way a weather report announces an unremarkable change in temperature. There was only the steady, procedural satisfaction of one more variable narrowed, one more source of potential incompatibility removed. Testing procedures, once standardized, brought their own particular rhythm to factories that adopted them. Before agreed specifications existed, each manufacturer had developed its own internal methods for verifying that a touch panel worked correctly, methods that varied enough between companies that a panel judged acceptable by one factory's standards might be rejected by another's more stringent internal checks, or conversely, might pass one factory's loose tolerances while failing to meet what a more careful buyer actually required. Standardized testing changed this. A panel could now be evaluated against a shared, published procedure, its results expressed in terms any buyer, regardless of which factory had produced the component, could interpret consistently. Consider what such a standardized test actually involved mechanically. A robotic arm, calibrated to apply a precise, repeatable amount of force, would press against defined points across a panel's surface in a fixed sequence, moving with a steady, unhurried mechanical precision that no human tester, however careful, could fully replicate across thousands of repetitions. Each contact point would be logged, the resulting registered coordinates compared against the intended target, with any deviation beyond an agreed tolerance flagged as a failure. The arm's motor produced a faint, consistent whir as it moved between points, a sound that became, in factories where this testing ran continuously across long shifts, a kind of ambient background rhythm, steady and unchanging, punctuated only by the occasional pause when a panel failed and was set aside for closer inspection. Environmental testing followed a similarly standardized path. Panels destined for markets with harsher climates were placed inside chambers capable of cycling through extremes of temperature and humidity far beyond what any ordinary room would experience, simulating years of environmental stress compressed into days or weeks of accelerated testing. Through a small viewing window in the chamber's door, a technician could watch condensation form and evaporate across the panel's surface as the internal climate cycled, the glass fogging briefly before clearing again as the chamber's heating elements brought the temperature back up. These cycles repeated dozens, sometimes hundreds of times, and only panels that emerged from this process, still functioning within specification, were approved for markets where such environmental extremes might genuinely be encountered during ordinary use. What standardization ultimately provided, beneath all of this procedural detail, was something closer to trust distributed across an entire industry. A device manufacturer sourcing panels from a supplier they had never directly visited could nonetheless trust that a panel meeting a published specification would behave predictably, would integrate correctly with their existing designs, would withstand the environmental conditions their published standard claimed it would withstand. This trust, built slowly through the unglamorous accumulation of shared testing procedures and agreed tolerances, allowed an industry that had begun in scattered, disconnected laboratories to eventually function as something resembling a single, coordinated system, each participant relying on specifications that no single company had created alone, but that the industry as a whole had gradually, carefully, and quite deliberately built together. Somewhere in this long process, a subtle shift took hold within the culture of the companies involved. Engineers who had once viewed a competitor's factory as an entirely separate world, operating by unknown internal rules, now found themselves reading the same published specifications, calibrating equipment against the same reference standards, attending the same working group meetings year after year until familiar faces from rival companies became, in an odd way, colleagues in the narrow sense of shared technical problem solving, even while remaining commercial rivals in every other respect. This peculiar dual relationship, competition in the marketplace, paired with quiet cooperation on shared technical foundations, would become a defining feature of how this industry continued to mature in the years that followed, each company building its own distinct products atop a common, carefully negotiated technical bedrock that none of them could have built as reliably alone or as quickly, working in isolation behind closed doors. There is a particular kind of change that happens so gradually across so many small increments that no one living through it can point to the exact moment it occurred. The shift from mechanical buttons to touch as the primary way people interacted with everyday devices belongs to this category of change. It did not arrive with a single announcement or a single dramatic demonstration that reordered the world overnight. It arrived the way a tide arrives, one small wave at a time, each wave unremarkable on its own, the cumulative effect only visible in retrospect, once enough waves had passed that the shoreline itself had quietly moved. Consider the ordinary devices that populated daily life during this transitional period. A device might retain its physical keypad for years after touch sensing had become reliable enough to replace it, not because the technology was lacking, but because the manufacturer's existing tooling, their existing supplier relationships, their existing engineering expertise, all remained oriented around the mechanical approach they had spent years refining. Switching to touch meant more than adopting a new component. It meant retraining assembly workers, renegotiating supplier contracts, redesigning internal circuitry to accommodate a fundamentally different kind of input signal. For a company with a functioning product and a stable market, this kind of wholesale change carried genuine risk, and many companies, quite reasonably, chose to wait, watching how early adopters fared before committing their own resources to the shift. This waiting period produced a curious intermediate landscape, one where mechanical and touch interfaces coexisted not just across different products, but sometimes within the very same product line. A manufacturer offering both a traditional keypad model and a touch-enabled model side by side, allowing the market itself to gradually indicate which approach customers actually preferred. Sales figures from this period, where they survive in old catalogs and internal reports, tell a story of slow, uneven preference. Touch-enabled models selling well in certain markets and demographics, while traditional models continued selling steadily in others, particularly among users who had grown comfortable with the tactile confirmation a physical button provided and felt, understandably, a certain hesitation toward a surface that offered no such confirmation beyond a visual or auditory cue. That hesitation deserves attention because it reveals something important about how deeply embedded tactile feedback had become in the ordinary human experience of operating a machine. A physical button, pressed, offers an unambiguous signal through the fingertip itself. A small give, a click, a return to its resting position. Each stage a wordless confirmation that an action has been registered before any visual indicator even has time to change. Early touch surfaces offered none of this. A finger pressing against smooth, unyielding glass, received no such confirmation through touch alone, and users accustomed to decades of button-based interfaces sometimes found themselves pressing twice, uncertain whether their first touch had registered, glancing anxiously at the screen for a visual cue that a physical button would have made unnecessary. Engineers working to smooth this transition understood that solving the underlying sensing technology was only half the challenge. The other half was cultivating, gradually and patiently, a new kind of trust between a person's fingertip and a surface that offered feedback through entirely different senses than the ones people had relied on for generations. Some manufacturers attempted to bridge this gap through small, deliberate additions to the touch experience itself. A brief tone sounded the instant a touch registered, gave the ear a confirmation the fingertip could not provide. A slight, almost imperceptible flash of the display beneath the point of contact offered a visual echo of the action, quick enough to feel immediate rather than delayed. Some devices experimented with tiny mechanical actuators hidden beneath the surface, capable of producing a faint buzz or click, timed precisely to the moment of contact, an artificial recreation of the tactile confirmation a physical button had always provided freely, now engineered deliberately into a surface that had none of that feedback built into its underlying physics. These solutions varied considerably in how convincing they felt, and engineers spent considerable effort tuning the timing of these artificial cues, since a confirmation arriving even a fraction of a second too late could feel more disorienting than no confirmation at all, a mismatch between the felt moment of contact and the signal meant to acknowledge it. Beyond feedback, there was the question of what people actually needed to accomplish, and whether touch genuinely served those needs better than the mechanical interfaces it was gradually replacing. This was not a question with an obvious answer, and different categories of use revealed the answer differently. For tasks involving simple, discrete selections, choosing one option from a small set of clearly labeled choices, touch offered a clear advantage. A person could look at a screen, see the available options rendered directly where they needed to be pressed, and select one with a single, intuitive gesture, without needing to memorize which physical button corresponded to which function, without needing to glance away from the screen to locate a control by feel. For other tasks, the advantage was less clear-cut, at least initially. Typing extended text, for instance, remained genuinely difficult on early touch surfaces. A physical keyboard offered raised keys a person could locate by touch alone, without looking, developing over years of practice a kind of muscle memory that allowed skilled typists to produce text at considerable speed while their eyes remained fixed elsewhere. Early touch keyboards offered no such raised geometry. Every key looked and felt identical to every other key, a flat, undifferentiated surface where the only distinguishing feature was a printed label the eye had to actively locate and confirm before each keystroke. This made touch-based typing in these early years, noticeably slower and more error-prone than typing on a well-designed mechanical keyboard, and it would take considerable further refinement in software prediction, in key sizing, in subtle visual and auditory feedback, before touch-based text entry became genuinely competitive with its mechanical predecessor. This unevenness meant the transition unfolded at different speeds across different categories of device and different categories of task. Devices built primarily around simple selection and navigation, where a person browsed through visual options rather than composing extended text, adopted touch relatively quickly, since the technology's strengths aligned closely with what these devices actually needed to do. Devices built around extended text composition retained physical keyboards for considerably longer, their manufacturers correctly recognizing that touch, in its current state of development, simply could not yet match the speed and accuracy a trained typist could achieve on physical keys. This was not a failure of touch technology, so much as an honest recognition that different tasks impose different requirements, and that a single interface, however promising, rarely serves every possible use case equally well from the outset. Looking back at this period, what stands out is not any single decisive moment where touch definitively proves superior, but rather a long, uneven accumulation of smaller decisions, made independently by different manufacturers serving different markets, each responding to the particular balance of advantages and limitations relevant to their own products. Some manufacturers moved early, betting that users would adapt to touch's limitations in exchange for its advantages in simplicity and flexibility. Others waited, watching the market's response before committing their own resources. Neither approach was objectively correct in every case. The transition succeeded not because touch was universally superior from its earliest days, but because it was patient enough, refined gradually enough, that it eventually became superior for a widening range of tasks, one incremental improvement at a time, until the mechanical interfaces it had once coexisted alongside began to feel, to a new generation of users, like unnecessary complexity rather than reassuring familiarity. There is something worth sitting with in this pattern, a lesson that extends well beyond the particular history of touch surfaces. Meaningful change in how people interact with their tools rarely announces itself. It accumulates instead in the small, unremarkable choices made by engineers solving narrow problems, by manufacturers weighing modest risks, by ordinary users gradually growing comfortable with something unfamiliar until it no longer feels unfamiliar at all. The keypad did not vanish in a single afternoon. It receded slowly, model by model, market by market, until one day, without any particular ceremony, it had simply become the exception rather than the rule, remembered fondly by those who had grown up pressing its firm, familiar keys, and entirely unknown to those who came after. A touch surface no matter how refined, is only ever the visible tip of a much larger and less visible system. Beneath the glass a person touches lies a layered architecture of supporting infrastructure, most of it entirely invisible during ordinary use, quietly performing the calculations and translations necessary to turn a fingertip's brief contact into a meaningful response. Understanding this infrastructure means looking past the surface itself and into the specialized components, manufacturing processes, and software systems that had to mature in parallel before touch could become something ordinary people encountered dozens, eventually hundreds of times each day without a second thought. Consider the controller chip, a small component often no larger than a fingernail, mounted quietly on a circuit board somewhere behind the display, tasked with the continuous, rapid work of monitoring the touch surface for changes in electrical characteristics and translating those changes into coordinates a larger system could interpret. This chip operated at a scanning rate measured in dozens of cycles per second, sweeping across the entire surface repeatedly, checking each region for the subtle electrical signature of an approaching or contacting fingertip, discarding the vast majority of readings that indicated no meaningful touch had occurred, and flagging the rare readings that did. The engineering challenge here was substantial. This scanning needed to happen quickly enough that a person's touch felt instantaneous, yet efficiently enough that the chip did not consume excessive power or generate excessive heat. Two considerations that pulled in opposite directions and required careful, iterative balancing across successive generations of controller design. Early controller chips were, by later standards, remarkably limited in their capabilities. They could typically track a single point of contact reliably, and attempts to register a second simultaneous touch often produced confused, unreliable results. The chip's underlying logic simply not built to disambiguate between multiple genuine contact points occurring at once. This limitation shaped, in turn, the kinds of interactions early touch interfaces could support. Gestures involving two or more fingers moving simultaneously, which would later become an ordinary part of everyday interaction, remained largely unavailable during this period, not because anyone had failed to imagine such gestures, but because the underlying controller hardware simply lacked the capacity to interpret them reliably. Engineers understood the limitation clearly and worked steadily toward controllers capable of tracking multiple contact points independently, a goal that required not just refined sensing hardware, but considerably more sophisticated signal processing logic, capable of distinguishing between two genuine fingertips and the various forms of electrical noise and interference that a busy, imperfect real-world environment inevitably introduced. The manufacturing of these controller chips followed its own quiet, specialized path, distinct from the manufacturing of the touch panels themselves. Semiconductor fabrication facilities, clean rooms maintained at exacting standards of dust control and environmental stability, produced these chips through processes involving multiple layers of material deposited and etched with extraordinary precision. Each layer built upon the last, according to a design that had to account not just for raw computational logic, but for the particular electrical sensitivity required to detect the faint signals a touch panel would send its way. Workers in these facilities moved through their shifts wearing full protective garments, their faces obscured behind clear visors, every surface around them designed to minimize the introduction of the microscopic particles that could, if allowed to settle onto a chip during fabrication, render an entire batch of components defective. The air inside these fabrication rooms carried its own particular quality, filtered and recirculated continuously through systems designed to remove particles far smaller than anything the human eye could perceive, producing an environment cleaner, in a strictly measurable sense, than most operating rooms in a hospital. The hum of these filtration systems formed a constant, low background presence, steady enough that workers stopped consciously noticing it within their first weeks on the job, the way anyone eventually stops noticing a sound that never varies or stops. Beneath this hum, more specialized equipment performed its work in near silence. Precision tools depositing layers of material only a few atoms thick, guided by systems calibrated to tolerances that would have seemed almost fantastical to the engineers who had built the very first crude touch prototypes only years earlier, working with sheets of glass wired by hand on cluttered laboratory benches. Software formed the second, equally invisible half of this supporting infrastructure, and its development followed a path just as gradual and iterative as the hardware it depended upon. In the earliest years of touch-enabled devices, the software responsible for interpreting a raw touch signal and translating it into a meaningful action was often minimal, doing little more than mapping a set of coordinates to a corresponding region of the screen, checking whether that region matched a predefined button, and triggering the associated function if it did. This was functional, but it treated touch essentially as a substitute for a mouse click or a physical button press, translated into a new physical form without meaningfully rethinking what touch, as a distinct kind of interaction, might actually be capable of supporting. Gradually, software engineers working closely with the hardware teams began to recognize that touch carried information a simple button press never could. A touch was not a single, instantaneous event, but a continuous stream of positions, a finger moving across a surface in a fluid path that carried direction, speed, and duration, all of which could be captured and interpreted if the underlying software were built to pay attention to more than a single point of contact and release. This recognition led to the gradual development of gesture recognition, software logic capable of distinguishing a simple tap from a sustained press, a quick flick from a slow, deliberate drag. Each pattern of movement mapped to a distinct action a user could learn to associate with a particular, intuitive, physical motion. Building this gesture recognition reliably required considerable trial and error, since human movement, even when performed with clear intention, rarely produces perfectly clean, geometrically precise input. A person intending to draw a straight line across a screen would inevitably introduce small deviations, tiny tremors and corrections the hand made unconsciously as it moved. Software needed to distinguish between these natural, harmless variations and genuinely different gestures the user actually intended, a task that required increasingly sophisticated filtering and pattern recognition, refined across many iterations as engineers studied recordings of real users interacting with real prototypes, noting where the software correctly interpreted intention and where it stumbled, misreading a slightly curved tap as the beginning of a drag, or hesitating too long before recognizing a quick, deliberate flick. The accumulated result of this software development, layered atop the accumulated result of the hardware development happening in parallel, was a system whose complexity vastly exceeded what any single component within it might suggest on its own. A user pressing a finger against glass triggered, in rapid succession, an electrical change detected by a sensing layer, a signal processed by a controller chip, scanning dozens of times each second, a coordinate calculated and passed to a software layer built to distinguish genuine gestures from incidental noise, and finally an action executed and rendered back to the display, the entire sequence completing quickly enough that the person touching the glass perceived no delay at all, no sense of the elaborate, layered infrastructure working invisibly beneath their fingertip. This invisibility was not accidental. It was the entire point, the hard-won result of years spent refining every layer of this system until the complexity beneath the surface became, for the person using it, simply and reliably disappeared. There is a particular satisfaction for the engineers who built these layered systems in achieving exactly this kind of disappearance. Success in this line of work is measured not by what a user notices, but by what a user fails to notice at all. A well-designed gesture recognition system draws no attention to itself. It simply works again and again in ways so consistent that the underlying complexity fades entirely from conscious awareness, leaving only the sensation of a direct, unmediated connection between intention and result. This was, in a sense, the ultimate fulfillment of the very question that had first prompted researchers to abandon buttons and switches in favor of direct touch. The desire to remove the felt distance between a person's intention and a machine's response, to close the gap not merely in principle, but in practiced, everyday experience, until touching a surface felt less like operating a machine and more like simply reaching out and having the world respond. No single region of the world built this technology alone, and understanding how touch-sensitive surfaces spread from specialized laboratories into ordinary daily use requires following a supply chain that stretched across continents, each region contributing a particular kind of expertise, material access, or manufacturing capability that no single place possessed entirely on its own. This global distribution was not planned in advance according to any grand design. It emerged piece by piece as companies sought the most efficient combination of raw materials, skilled labor, and manufacturing infrastructure available to them, wherever in the world that combination happened to exist. Certain regions developed particular strength in the production of specialized glass, the foundational material upon which nearly every touch panel depended. Producing glass thin enough, strong enough, and optically clear enough for this purpose required furnaces and processing equipment representing decades of accumulated metallurgical and materials science expertise, concentrated in facilities that had often originally been built for entirely different purposes, producing glass for other industries before touch technology created a new and rapidly growing demand for their particular capabilities. Workers in these glass facilities described conditions shaped by intense, controlled heat, furnaces glowing with a steady orange intensity, visible even through the small viewing ports built into their casings, molten glass moving along production lines in slow, careful stages, cooling gradually under carefully monitored conditions to avoid the internal stresses that could cause a sheet to shatter unexpectedly, sometimes months after it had left the factory, if the cooling process had been rushed or handled incorrectly. Other regions specialized in the precise deposition of conductive coatings onto this glass, a process requiring vacuum chambers and specialized equipment capable of applying materials in layers only a few atoms thick, evenly across large sheets, moving continuously through the production process. This work demanded an entirely different kind of technical infrastructure than glass production itself, and facilities specializing in coating deposition often developed independently of the facilities producing the raw glass, connected across considerable distances by shipping routes that carried finished glass sheets, carefully packaged and cushioned against the vibrations of transport from one specialized facility to another before a single panel had even begun to resemble a finished product. Still, other regions developed expertise in the final assembly of complete touch panels, combining coated glass with the controller chips, connectors, and protective layers necessary to produce a finished component ready for integration into an actual device. These assembly facilities often employed large numbers of workers performing careful, repetitive tasks at production lines, moving at a steady, continuous pace. Each worker responsible for a narrow stage of the overall process, their individual actions accumulating, station by station, into a finished panel by the time it reached the end of the line. The rhythm of these facilities carried its own distinct character. The steady hum of conveyor systems, the periodic click of automated testing equipment, verifying each completed panel before it moved onward. The quiet concentration of workers whose hands had, through repetition, developed a practiced efficiency that no amount of instruction alone could have produced. Coordinating across this dispersed network of specialized facilities required its own quiet infrastructure, one built not from glass or silicon, but from logistics and communication. Shipping containers moved steadily between ports, carrying finished panels and raw materials alike, their journeys tracked and scheduled with a precision that had to account for manufacturing timelines spanning multiple facilities on different continents, each dependent on the timely arrival of components produced somewhere else entirely. A delay in one facility, a shipment held at a port for inspection, a furnace requiring unexpected maintenance could ripple forward through the entire chain, arriving eventually as a shortage at an assembly facility thousands of miles away, waiting for glass that had not yet completed its journey. Managing this complexity became its own specialized discipline, one that grew increasingly sophisticated as the volume of touch panels moving through this global system expanded from a modest trickle into a substantial, continuous flow. Beyond the physical movement of materials and components, a second, less visible kind of global connection was forming during this period, one built from shared knowledge rather than shared supply chains. Engineers working on touch technology in one country regularly encountered, through published research and international conferences, the work of colleagues operating under entirely different economic and institutional conditions elsewhere. A researcher working within a well-funded corporate laboratory might find themselves reading with genuine interest a paper produced by a university team operating with far more modest resources, discovering an elegant solution to a shared technical problem that no amount of funding alone had managed to produce internally. Knowledge, unlike raw materials, did not require shipping containers or customs clearance. It moved through journals, through conference proceedings, through the increasingly common practice of researchers relocating between institutions in different countries, carrying with them not physical components, but accumulated understanding. International conferences during this period became particular sites of this quiet exchange, gathering researchers and engineers from dispersed institutions into shared rooms for a few concentrated days each year. Presentations followed a familiar rhythm. A researcher would step to a podium, project a series of technical diagrams onto a screen behind them, and walk an audience through months or years of accumulated laboratory work condensed into a 20-minute summary, followed by a period of questions from an audience that often included direct competitors, each probing gently for details the presenter might not have intended to share so openly. The hallways outside these formal sessions carried their own significance. Informal conversations conducted over cups of coffee, business cards exchanged, tentative collaborations proposed between researchers who had never previously known of each other's existence, connections that would sometimes, months or years later, produce joint publications or shared patents. Neither party could have developed entirely alone. This international exchange was not without friction. Different countries maintained different intellectual property regimes, different expectations around what could be freely shared in a published paper versus what needed to remain protected within a company's internal research. Researchers navigating these differences sometimes found themselves caught between the collaborative instincts of the broader scientific community and the more guarded instincts of the commercial organizations funding their work. A tension that shaped, in subtle ways, exactly how much technical detail made its way into any given published account. Some breakthroughs, achieved quietly within corporate laboratories, remained undisclosed for years, protected by patent filings rather than published papers, emerging into public knowledge only once a company judged the commercial advantage of secrecy had run its course. And yet, despite these frictions, the overall trajectory of this period was one of gradual, accumulating convergence, ideas and techniques flowing across borders with increasing ease, manufacturing capabilities distributed across a widening network of specialized facilities, each region contributing its particular strength to an increasingly interconnected whole. By the time touch-sensitive surfaces had become an ordinary feature of everyday devices, the technology inside any single such device typically represented the accumulated contribution of researchers, engineers, and manufacturing workers spread across a dozen or more countries, each unaware of most of the others, each contributing a small, essential piece to a whole. None of them could have built alone, in a single laboratory, within a single national tradition of engineering practice. There is something quietly remarkable in this fact, easy to overlook precisely because the finished object gives so little indication of the distance its constituent parts have traveled to arrive together. A person holding a completed device rarely pauses to consider that the glass beneath their fingertip may have been formed in one facility, coated in another, fitted with a controller chip designed in a third location and manufactured in a fourth, assembled finally in a fifth, each stage separated by considerable distance and yet somehow arriving, in sequence, at a single point of final integration. The device asks nothing of its user beyond a touch. It offers no visible record of the journey that preceded that touch becoming possible, no acknowledgement of the thousands of individual hands and countless separate decisions that had to align across years and across continents before a single fingertip could press against glass and expect, with quiet confidence, a reliable response. Step back far enough from the wires and coatings and controller chips, and a different, quieter question comes into view, one that belongs less to engineering and more to the study of how people relate to the tools they use. What does it actually mean for a technology to disappear into intuition, to become so natural that using it no longer feels like using a technology at all, but simply like reaching out and interacting directly with information itself? This question occupied a particular kind of thinker during the years touch technology matured. People who worked alongside the engineers but approached the problem from a different angle entirely, asking not how to make a surface sense a fingertip, but what it meant, philosophically and psychologically, for a fingertip to reach toward a surface, expecting a response. There is a long history, predating touch technology by centuries, of human beings extending their sense of self and agency into the tools they hold. A skilled craftsman working with a familiar tool often describes a sensation of the tool becoming, in some meaningful way, an extension of the hand itself, its weight and resistance no longer registering as separate from the body wielding it, but integrated into a single fluid sense of capability. Touch technology, at its best, aimed for something similar, though achieved through an inversion of the usual relationship. Rather than a tool extending the reach of the hand outward into the world, a touch surface invited the hand to reach directly into a space of information and possibility that had, until that point, always required some intermediary object to access. This inversion carried subtle but significant implications for how people came to understand their relationship with the devices surrounding them. A person operating a machine through a keyboard or a set of physical buttons maintains, almost inevitably, a certain psychological distance from the machine's inner workings, aware, even if only faintly, that their actions are being translated through an intermediate mechanism before producing an effect. A person touching a screen directly, watching an object move precisely as their finger moves, dragged smoothly across the surface in continuous correspondence with the motion of their own hand, experiences something closer to direct manipulation, a sensation that the boundary between intention and effect has narrowed to something approaching immediacy. Researchers studying human-computer interaction during this period took this observation seriously, recognizing that the psychological experience of using a technology mattered as much as its raw technical capability, that a system capable of registering touch accurately but responding with even a slight perceptible delay could feel less satisfying to use than a system with marginally less precision but noticeably faster, more immediate feedback. This recognition shaped design priorities in ways that were not always obvious from the outside. Engineers sometimes found themselves trading raw sensing accuracy for perceived responsiveness, understanding that a slightly less precise touch registration responded to instantly would generally feel more satisfying to a user than a more precise registration, burdened by even a small additional processing delay. The felt experience of immediacy, it turned out, mattered more to most users than an abstract standard of technical precision they had no direct way of perceiving or measuring for themselves. This tension between measurable accuracy and felt experience produced, within engineering teams, a kind of internal negotiation between disciplines that did not always share a common vocabulary. A hardware engineer, trained to think in terms of tolerances and error margins, might view a small increase in positional inaccuracy as an unambiguous regression, a step backward from an established technical benchmark. A researcher focused on human perception might view the same trade-off quite differently, pointing to studies showing that users, when asked to compare two systems in blind testing, consistently preferred the faster, slightly less accurate one, describing it using words like natural or responsive, without any conscious awareness of the underlying trade-off that had produced this preference. Resolving these disagreements required teams willing to treat subjective human experience as a legitimate engineering constraint in its own right, worthy of the same rigorous testing and iteration typically reserved for more easily quantified metrics like sensing precision or manufacturing tolerance. There was also, within this philosophical dimension of the technology's development, a quieter conversation about accessibility, about who this new mode of interaction served well and who it might inadvertently exclude. A physical button offers a distinct advantage that a flat touch surface, by its nature, struggles to replicate. It can be located and operated by feel alone, without requiring sight, a property that had long made mechanical interfaces workable for people with visual impairments who could learn the position of a familiar control through touch and muscle memory, operating a device confidently without ever needing to look directly at it. Early touch surfaces, offering no raised geometry, no distinguishing tactile landmarks across their smooth, uniform expanse, initially represented a step backward for this population, a well-intentioned advance in usability for some users that inadvertently narrowed usability for others. This concern did not go unaddressed, though addressing it required years of dedicated design work running alongside the more visible, mainstream development of touch technology. Researchers and advocates working specifically on accessibility began developing alternative approaches, audio feedback that could describe aloud whatever element a finger happened to be resting on before a selection was confirmed, allowing a person to explore a screen's layout through sound rather than sight, gradually building a mental map of where different functions were located. Software began incorporating deliberate pauses between initial contact and final selection, requiring a distinct, separate confirming gesture before an action took effect, reducing the risk of accidental selections for users navigating primarily through auditory rather than visual feedback. These adaptations required genuine collaboration between engineers focused on the underlying sensing technology and specialists focused specifically on the needs of users who could not rely on vision alone. A collaboration that, when it worked well, produced interfaces meaningfully more capable than either group could have designed independently. This accessibility work carried a broader lesson that extended well beyond the specific needs of any single population of users. It revealed that touch technology, for all its promise of directness and intuition, was never actually neutral in how it distributed its benefits. Every design choice, however small, quietly favored certain kinds of bodies, certain kinds of sensory capabilities, certain kinds of prior experience with similar technologies over others. A surface that felt effortlessly intuitive to one person might feel confusing or even unusable to another, not because of any flaw in that second person's capability, but because the interface had been designed, whether deliberately or by unconscious default, around assumptions that did not describe everyone equally well. The most thoughtful engineers working in this space came to understand intuition itself, not as some fixed, universal property a good interface simply possessed, but as something constructed carefully through deliberate design choices that could either widen or narrow who exactly found a given interface intuitive to use. This deeper understanding did not arrive quickly, nor did it arrive uniformly across every company and every product. But its gradual influence can be traced through successive generations of touch-enabled devices, each iteration incorporating lessons learned from the population of users the previous generation had, whether through oversight or genuine difficulty, failed to fully serve. Consider, too, the quieter matter of age, another dimension along which touch technology's supposed universality proved more complicated than early enthusiasm sometimes suggested. Older users, who had spent decades developing familiarity with mechanical interfaces, sometimes found the shift to touch less intuitive than younger users encountering the technology for the first time, without any competing mental model to unlearn. A generation raised on the definite, confirming click of a physical button sometimes approached a flat, silent surface with a hesitation that had nothing to do with any deficit in capability, and everything to do with decades of accumulated expectation about how a machine ought to respond to a deliberate press. Designers who took this seriously began building in longer tolerance windows for touch duration, larger target areas for interactive elements, and clearer visual confirmation of registered actions. Small adjustments that made touch interfaces meaningfully more welcoming to users who had not grown up alongside the technology's earliest, roughest iterations. Every mature technology eventually invites a particular question from those who have spent years refining it. What comes after this? For touch surfaces, having traveled such a long and gradual road from crude laboratory prototypes to something used almost unconsciously by enormous numbers of people every day, this question arrived not as anxiety, but as a kind of natural curiosity, the same restless spirit of inquiry that had driven the technology's development in the first place, now turning its attention toward whatever limitations remained in the current approach and whatever new possibilities might lie just beyond them. One direction this curiosity pursued involved the question of pressure, of whether a surface could sense not merely where a touch occurred, but how firmly it had been applied. Early touch technology, in both its capacitive and resistive forms, generally registered a touch as a simple binary event, contact or no contact, present or absent, with little attention paid to the subtle variations in force a person might apply. Yet human hands are capable of remarkable gradations of pressure, and researchers began to wonder what new forms of interaction might become possible if a surface could distinguish a light, tentative touch from a firm, deliberate press, translating that distinction into a correspondingly nuanced response. Perhaps a gentle preview triggered by a light touch, followed by a more definitive action. Only once sufficient pressure confirmed genuine intent. Developing reliable pressure sensing required solving problems distinct from those that had occupied the earlier decades of touch development, where earlier work had focused on locating a point of contact accurately. This new direction required measuring force with similar precision, a challenge that involved new materials capable of subtly deforming under pressure in ways that could be measured electrically, or new arrangements of existing sensing layers capable of detecting the slight change in contact area that occurs as a soft fingertip flattens under increasing force. Early prototypes exploring this direction were, as with every generation of new capability in this technology's history, imperfect and inconsistent, sometimes registering false positives from ordinary light contact, sometimes failing to distinguish clearly between two different levels of intended pressure. But the underlying research continued steadily, following the same patient, iterative pattern that had characterized every prior advance in this field, each small improvement building carefully upon the last. Alongside pressure, researchers pursued a parallel direction, focused on what happened just before contact, the brief moment when a finger approached a surface without yet touching it. Some of the earliest capacitive sensing technology had, in principle, always been capable of detecting proximity to some limited degree, since the underlying electrical field, a fingertip disturbed, began shifting even before actual contact occurred. Refining this capability opened the possibility of surfaces that could respond subtly to an approaching finger before the moment of contact itself, perhaps highlighting an element about to be selected, offering a small preview of an impending action, extending the interaction beyond the single, discrete moment of touch into something closer to a continuous, evolving conversation between hand and surface. This pursuit of pre-contact sensing raised its own set of quiet engineering questions. How close did a finger need to be before its presence should register? How should the system distinguish an intentional approach, a hand deliberately reaching toward a specific target, from the incidental proximity of a hand simply resting nearby or passing over the surface on its way to something else entirely? Researchers spend considerable time studying the natural patterns of human hand movement, observing how people actually reach toward objects in ordinary use, noting the subtle differences in trajectory and speed between a deliberate, targeted approach and an incidental, passing motion. Information that fed directly into the algorithms eventually built to make this distinction reliably, without requiring the user to think consciously about the difference at all. The entire system quietly inferring intent from the shape and pace of an ordinary, unremarkable gesture. Perhaps the most significant direction this ongoing curiosity has pursued involves questioning whether touch itself, however refined, represents a final destination or simply another way station along a longer journey. Some researchers, reflecting on the original motivation that had driven the earliest work in this field, the desire to close the distance between human intention and machine response, began to ask whether touch had actually closed that distance completely, or whether it had merely narrowed a gap that other emerging approaches might close further still. A fingertip pressed against glass still requires a physical action, still requires the hand to move across space before intention can register. Researchers exploring gesture recognition through cameras or the interpretation of subtle muscle movements detected without any surface contact at all wondered whether these newer approaches represented a further evolution of the same underlying impulse that had first motivated touch technology decades earlier, each generation seeking to remove one further layer of mediation between what a person wants and what a machine understands. This kind of speculation, common among researchers reflecting on a mature technology, carries a particular humility worth noting. The engineers and researchers who built the earliest touch prototypes, wiring crude grids by hand in laboratories lit by fluorescent tubes, could not have predicted with any confidence exactly how their work would eventually be used, or how thoroughly it would embed itself into the ordinary rhythms of daily life across the world. Their contribution was narrower and more modest than any grand vision, solving a specific, immediate problem, closing a small technical gap, refining a material property by a fraction of a percentage point. It was only through the patient accumulation of thousands of such modest contributions, made across decades and across continents, that touch technology gradually became something recognizable to anyone reflecting on its history today. There is a quiet lesson embedded in this pattern, one that extends beyond the particular history of touch surfaces into a broader understanding of how meaningful technological change actually occurs. It rarely arrives through a single, decisive breakthrough. However much later, retellings might simplify a complicated, gradual history into a cleaner, more satisfying narrative, centered on a single moment or a single inventor. It arrives instead through the accumulated labor of countless people working on narrow, specific problems, most of whom never fully grasped the eventual scale of what their small contribution would help build. Consider one final time the full arc this narration has traced. A room full of dials and switches, and the quiet frustration of engineers who sensed that something better might exist just beyond the reach of mechanical translation. Laboratories where crude grids of wire taped to workbenches first proved that a fingertip alone could speak to a machine. Years of patient refinement, coating thicknesses adjusted by fractions of a millimeter, testing chambers cycling through artificial seasons to prove a surface could withstand the ordinary world. Standardization meetings where competitors sat across the same table, gradually agreeing on shared foundations. The slow, uneven migration away from buttons, met with hesitation from users whose hands had trusted mechanical feedback for a lifetime. A global network of glass furnaces, coating chambers, and assembly lines, each specialized facility contributing a peace no other facility alone could provide. And beneath all of it, a quieter conversation about what intuition means and who gets included when a new interface is called natural. The glass beneath a fingertip today carries within it the accumulated patience of researchers testing coatings in quiet laboratories, of factory workers calibrating equipment through long, careful shifts, of standardization committees negotiating over the precise spacing of a connector's pins, of accessibility advocates insisting that intuition be built to include rather than exclude. Each touch, however brief and unconsidered it might feel in the moment, rests upon this long, quiet accumulation, a history embedded invisibly within an object that asks nothing more of its user than the simple, ordinary act of reaching out and touching. And so, the narrative of this assembly comes to its quiet conclusion. Whether you are still awake, or whether you have already drifted into a deep and peaceful sleep, know that you are exactly where you need to be. The world is vast, but tonight, its systems are simply the backdrop to your rest. Thank you for joining me here at Quietly Made. Rest now. Join us again tomorrow. Good night.